The title of this video is Variable Fluid Properties Test Case 1. This video comes behind a number of other videos that I have made recently discussing energy and surface integrals. And this particular test case is kind of exhibit what we learned in those test cases. My name is Jeff Franklin. I'm the primary architect of the commercial software package called Azore, a CFD tool specifically designed for solving industrial level problems. If you're interested in this software package, please visit the website azorecfd.com. So we're first going to start this discussion by reviewing the geometry of this test case, and here is kind of a schematic of the geometry. This is the flow domain, and what we have here is some ductwork that passes through some tube bundles and then out an inlet here. And so we have two flow inlets. We'll call it inlet 1 and inlet 2. And then this flow comes down and then it passes through tube bundle 1 and tube bundle 2. And after it leaves tube bundle 2, it then goes through a few flow distribution devices, some angle irons, and some blocker bars. For the purposes of this discussion, we're going to assume that these division baffles inside the tube bundle are perfectly isolated, so no energy will transfer across these thin walls. We're also going to assume that there's no heat transfer going to the exterior world here in this model. So it really makes this into a mixing and heating problem, where mixing of these two streams right here, these two fluid streams, and then the heat transfer that might take place within each of these tube bundles. So, but what we're really interested in is what kind of value will you get when you do surface integrals, and we've picked a number of planes here through this geometry, and these red lines kind of represent where we might want to take a surface integral to get some sort of average value. And so there are three planes chosen kind of in this entry mixing area. Then there's a plane chosen right here, right on the entrance to tube bundle 1. And then at the exit of tube bundle 1, we have another integration plane. And then another one, we'll call it P6 here at the exit of tube bundle 2, and then P7 is an integration plane kind of in the middle of whatever flow structure develops here, and then P8 and 9 on either side of the angle irons, and then the final one after the blocker bars we will call P10. So that's kind of, that's our geometry and the integration planes that we are going to explore, and we're going to run a number of different simulations looking at different ways one might model this environment. So for the first case, we're going to kind of assume that there is no heat transfer in any of the bundles. And so we'll just start over here on the left-hand side, and we'll assume, for instance, we have hot water vapor or steam coming in at the top, and it's basically a 0.5 kilogram per second at 1,000-ish degrees K. Down at the bottom, here's our cool gas stream, and this is hot, hotter air, but not as hot as the steam, and it's also coming in at 0.5 kilograms per second. So the mass flow rate between these two streams is the same. The temperature is just different. To give an idea of what the length scale of this geometry is, it's about 1.5 meters tall here. And for this particular case, we're going to assume that no heat transfer occurs in these bundles. And so it really comes down to be a mixing case where these two hot and cold gas streams that are dissimilar from one another in the fact that one's steam and one's air mix with one another as it passes through this geometry. Since this is a heat transfer problem, we're going to use our material properties are all going to be variable with temperature. They will also be variable with mixture. So the specific heat will depend both on temperature and of, its composition of air and steam. So to kind of get a good idea of what this flow structure might look like, we're going to look at some of the predictions that Azore has made. And so here is a simulation that's brought up in Azore, and this is the geometry. And one thing that might be interesting to do is look at path lines as they start from this inlet right here. And so we can look at path lines here, and this is you can see how they pass through here, but perhaps we would want to color them a little bit differently. For perhaps the lower ones, we would want to make them look cold. So maybe we would choose a color of, say, blue. Okay, so now we have blue path lines inside this geometry. You can see how the fluid path line, as it comes around here, this is kind of where the steam might go, and the blue ones are where the air might go. And we can animate this if we would like, and kind of look and see where they go and see where, you can see that the steam is traveling a lot faster than the air by the length of these path lines. So this is kind of one way we could look at the flow structures in here. There are also other ways that we might want to look at the flow structures. One of them would be to look at it using contours. And say, for instance, the velocity profile, we might want to look at the velocity. And here is the total velocity flow field of the gases. And you can see here that the higher velocities of the steam are shown here by the kind of greenish areas, and the bluish areas of lower velocities of the air coming in, you can see there. But then you can see how as these two gas streams mix, they kind of pass through and get spread out by the tube bundles. But one thing that's kind of interesting to look at, this is the velocity magnitude, but maybe it's a little bit interesting to look at the directionality. So maybe we could go ahead and turn on velocity vectors. And so here we can quickly put some velocity vectors on top of this to look at them. And we can do various things to make these velocity vectors look like we might want. Perhaps we would want to look at more velocity vectors where we would increase the distribution there. So here we make the distribution a little bit finer and we can see more of them there. Or maybe we would like to look at a little bit coarser one. We can also adjust the length of the arrows kind of dynamically. So we can kind of play around with this until we get something that looks like, visually appealing, and it helps us get a feel for what this looks like. So that's another thing that we can look at, and we can kind of get a feeling for what the flow structures look like in here. As you can see, the arrows are kind of spreading out, going around here. But this is one of the flow structures that I guess is a little bit interesting. We have kind of a recirculation zone that develops as the flow exits tube bundle 1. So, but there are other things that we might want to look at as well using our contours. Say, for instance, we might be interested in the temperature distribution in here and how the mixing process moves and distributes the energy and the temperature, the resulting temperature there. And here you can see where it comes in hot and cold, and you can kind of see this is the line where the two are mixing, and then the mixing process kind of proceeds until it's fairly uniform by the time it leaves this domain. We can also look at the mixture fraction, so we can kind of differentiate between these two gas streams and how they mix together. The red lines here represent the water vapor or the steam, and you can see it's a value of 1 here. 1 meaning that it's a fraction value, so that means that it's all steam right here, and 0 means it's all air down here. Another thing that might be interesting to look at are the material properties. Here we can look at the specific heat, and here we're looking at the calculated specific heat. The specific heat that is represented not only by the temperature, but the mixture. So like in this area, this is the specific heat at that temperature, but as well as the mixture of the different compositions of the steam and the air at this location. And we can look at all kinds of, we could perhaps look at the density. Where the air comes in at a low temperature, the density is higher, and then we can see how the density changes as it passes through this domain. So this is just kind of a way of how we use our CFD tools to get a flavor visually of what the flow structures look like, but we would use surface integration tools to get precise numbers. And so now let's take a look at that, and we're going to use some surface integrals, and there are a number of different types of surface integrals you can perform. One of them is an enthalpy balanced surface integral where you would expect the values to really honor what you would expect from a conservation of energy standpoint here. And so the way this method works is you would start by kind of integrating the energy flux through a surface. And once you have that energy flux, you would divide it by that system mass flow. And so when you do that, you get an enthalpy value that is kind of an average value of the energy flux through the surface. And then you can take that average enthalpy and you can use the lookup representation between temperature and enthalpy to find a representative average temperature that is going to be kind of the temperature you would expect from an energy conservation standpoint. But there are other methods that you might want to use as well. Another method would be a mass flow rate weighted temperature, depending on how you want to look at the average temperature. And this method basically takes the temperature at each location and multiplies it by the mass flow rate and then normalizes it by the total mass flow rate through the surface, and that gives you another average temperature value. Another method would be an area weighted temperature, where you would take the temperature multiplied by the surface area, you would add that up, and then you would normalize it by the total surface area. So these are three different methods that you could use to determine an average value on the planes that we kind of highlighted before. So in this case, we're really kind of interested in the energy equation, so we're going to look at what those values would be. And so what would the actual value be? What kind of value would we expect from an energy conservation standpoint? And we can actually determine that pretty easily by using our spreadsheet and some handbook calculations. So we know the mass flow rate and we know the temperature. And once we know the temperature, we can find the energy of the enthalpy level there. So that gives us, based on its temperature, this enthalpy level right here. And once we know the enthalpy level, we can use that in combination with the mass flow rate to find the energy flux of the water vapor coming in here. So, and we can do a similar calculation right over here to find the energy flux coming in from the air. And once we know the energy, the two energy fluxes, we know that the average value has to be kind of the average of both of these energy fluxes. So we can add those two energy fluxes together, this value, and you come up with an energy flux right over here of this value. Now, since our mass flow rate is 1, we can simply divide this by the mass flow rate, and we get the same value, only it's a joules per kilogram type number. And once we know that number, we can look up the temperature. So like if we look right here, our mixture enthalpy, which on average, it's going to be 50% air and 50% water. So, and that would be, here we have three curves. We have a curve for the air, which is the red line, a curve for the vapor, which is the blue line, and then we have a curve, which is the green line, which is halfway between. So we can look and take this energy value, and that's right around 800,000, and we can go over to our green line, and then maybe go up a little bit, and then come down, and we would expect a temperature right around 850 degrees. And if you precisely calculate that using your CFD tool, you would find that the number is precisely, based on an energy balance standpoint, going to be around 856 degrees Kelvin. So that is the average temperature that we would expect at every single plane from an energy conservation standpoint. So one of the things about Azore is that we provide tools that allow you to go and grab this information if you want, and you can use those through the JavaScript tool that we have. And so there are just two tools, these JavaScript objects here under Azore database. One of them is get enthalpy, where if you have the temperature, you can get the enthalpy of the fluid mixture that you have. The other one is if you want to go in the other direction, say for instance, you want to get the temperature representative of if you have the enthalpy value. So you would give the enthalpy and the mixture information there, and it would determine the temperature there, kind of like looking it up on that curve. So these are tools that are readily available within the Azore environment. So now let's just take a look at the integration that you would get on each one of these planes. And let's just say this P1 right here, that would be the integrated value right here. And in our table over here, here are the three temperatures that we would get. One of them, the ENT, this nth K, these are the enthalpy you would get in Kelvin from an energy conservation standpoint, and it is the 856 degree type number that we are expecting. If we use a mass flow rated average, we're going to get a temperature of 740 degrees. And if we use an area weighted average, we would get a value on the order of 482 degrees. And so, depending on what you're interested in looking at, one of these may be more appropriate than the other. But from an energy standpoint, we would expect, now if you kind of look down from an energy conservation standpoint, every single one of these planes throughout the whole system are all 856 degrees. But you can see that the temperature for the mass flow rate weighting or the area weighting, they vary significantly away from the mass, the conservative value that the mass conservative or energy conservative value that we would expect there. But once you get to the very end, as you would hope, when the value becomes an average value, these numbers once again become very close to one another. So in summary, we've kind of reviewed a mixing chamber that we're going to use to kind of evaluate different ways of modeling energy transfer in a two-bank system. We've used Azore to look at the velocity and mixture and temperature predictions that would happen for the particular case, the isothermal or the mixing only case. We've reviewed basically these surface integration methods that could be used to find average values on our integration surfaces. And then we reviewed the surface flux relationships there and how you would use the inlet fluxes and how we would come up with what, from a handbook, what kind of temperature we would expect there just by looking at the fluxes coming in there. And then we could see that the enthalpy-based methods really give the same temperature throughout the whole system, which is what we would expect. But the mass flow and area average values vary throughout the system because of the variation in the mass flow rates and the temperature distributions. That concludes this session right here. If you're interested in more technical content like this, please visit the website azorecfd.com. At YouTube, that's the channel there, so you can find other technical content like that. If you're interested in a CFD tool that really is geared towards solving industrial level problems, please visit the Azore CFD website, and so you can learn more information about that.